Okay, so yeah, I think we're back live again. Sorry for the interruption. So, today, what we are going to see in today's class, we are going to see these topics. Means, what is the variation of the value of G as we move upwards or downwards? Okay, what is gravitational field? What is gravitational field strength? Relation between field and potential, gravitational field and gravitational potential, gravitational potential energy and binding energy. In between, there is also one more topic, gravitational potential. Okay, so these are the few things we are going to see. Not few, they are quite things. We are going to study this. Okay, so let's start. For example, this is our Earth. A guy or any body or someone is on the surface, right? So what is the value of G they are going to experience? The value of G they are going to experience is 9.81 meter per second square. Correct? What if this guy is floating around in space? Okay, what if he's floating around in space? So the value of G, what will be the value of G? Acceleration due to gravity? We don't know. Okay, is it 9.81? Is it something different? We don't know. What if this guy decided to dig a hole inside the earth? Okay, he dig a hole inside the earth, and what will be the value of G for this person when he reaches inside the earth? Okay, so in these cases, we are going to find out how gravity varies. Okay, so let's start. Let's first start with the body going above the height. Okay, for example, if I take the example of this is a surface. Okay, I think there's something wrong. Yeah, I think it's right. So, for example, if let's say at this point, which is at height h, okay, and let me draw the Earth first. Let me take the example of Earth. So this is our Earth, okay, and at this point, at a height of h, we want to calculate the value of G. Okay, so how do we calculate it? It's pretty simple. Let us first consider what is the value of G on the surface. Just remind me the formula. G is equals to G mass of Earth upon R square. Yes or no? Okay. Now what we are going to see, what will be the value of this? How did we get to this value? First tell me. How did we get to this value G equals to? What we did was we took F is equals to G M1 M2 by R square, and we took F is equals to MA MG, right? We equated these two and we got this value. Correct. Now same thing we are going to do. From the center, the distance here is R. Yes or no? From the center distance, the total distance from the center of the Earth, the value of R will be, for this case, capital R plus small h, right? R is the distance from the center to our point, to our point where second mass is kept. Okay, first mass is the mass of the Earth. So I'm writing it ME. Second mass is mass we are observing the value of G on. So what is the distance between the center of the first mass and the center of the second mass? It is R plus capital H. So this is the value. Now substitute it here. F dash is equals to G mass of Earth, mass of second body upon R plus H whole square. Yes or no? Now, what we are going to do on this body, what will be the force? F is equals to M2 into G dash. What is G dash? G dash means the difference, means the different acceleration due to gravity that is acting. As simple as that. Equate these two. What will you get? You'll get G ME M2 by R plus H whole square is equals to M2G. So these two terms will cancel out. These two M2 gets cancelled out, and the value of G dash will be equal to G ME by R plus H whole square. Okay, what if, so this is the value. Okay, but what we want to do is we want to compare it with the initial value, means g, small g, 9.81. We want to compare it with that. So I'm going to take g, m, e and r square outside. So what will be the remaining inside? See, r and square got outside, right? So that will be h by r whole square. Hopefully this is clear. So can I say this value, this term is g? Yes or no? So just substitute g here, and I'll write this term as 1 plus h by r to the power minus 2. Now, we saw binomial expansion, right? What was binomial expansion of 1 plus x to the power whole n? That was 1 plus nx plus n minus 1 x square by 2 factorial and so on, right? Just substitute it here. What will you get? What is the value of n? I'm writing it down. The value of x here is h by r if you compare these two, and the value of n is minus 2, right? Value of x is h by r. Compare these two. See, h by r and x. And the value of power is minus 2 here. So value of n is minus 2. Substitute these values in the formula. You'll get 1 plus nx. N is minus 2. X is h by r, right? Plus n minus 2 minus 2 minus 1 x square means h by r whole square divided by 2 factorial and so on. Now, the value of h by r, okay, what we are going to do is we are going to neglect all these other terms. We are going to neglect all these other terms. Why? Because the value of h by r becomes very, very negligible for other terms, right? So we are going to neglect it. The only two terms are remaining. So what are the two terms? G 1 minus 2 h by r, right? G dash. This is our formula. When we are going to use this, when h by r is very, very less than 1, or I can say h is very much less than 1. Okay, when h is very much less than 1, we are going to use this formula. What if h is not very much less than sorry, h is very, very less than r? Okay, in other case, we are going to use the initial formula itself. So this is for this case. Keep it in mind. All right. And for other cases, we are going to use simple g dash is equals to g upon 1 plus h by r whole square. We are going to use this when h and r are of comparable lengths. For example, the value of r. What is the value of r? What is r? R is the radius of earth, right? Radius of earth. What is the value of radius of earth? 6400 kilometers. So what if I went 6500 kilometers up, or what if I went 6000 kilometer up? Then these two values are comparable, right? We are going to use this formula, not that one. Is that clear? Why is that? Is that clear? Because on expansion, we neglected it on the basis key this is very much less than r. H is very much less than r. All right. So hopefully these two formulas are clear. It's very important. Okay. Let's move on after that. Just note it down. Note these formulas down. I'm giving you 10 seconds. Yeah. I'm giving you 10 seconds to note these formulas down. Okay. Let's move on. Now, what we are going to do is we are going to go below the surface now, this time. All right. For example, this is our Earth. Okay. Let me just make a proper Earth so that you get a feel of Earth. Okay. So this is our Earth. And what this time, what we are interested in, we are going deep down. We are going to dig a tunnel. Okay. And it's not like 10 meters or 20 meters or 30 meters tunnel. It's like full in kilometers we are going to dig in. All right. So we are going to dig a tunnel inside like this. Let's say this is our tunnel. And let's say it is H or D depth inside. This tunnel is D depth inside. Okay, D depth inside. Now, this tunnel will cut out a portion. Okay, if this is the center, this tunnel will cut out a portion of the earth, right? Yes or no? Okay. If somebody is standing, let's say at this point, in the end of the tunnel, what will they experience? They'll experience a force F dash that is due to this inside part, right? On the center. Okay, so F dash is equals to G, mass of cutout portion into mass of that guy upon R square. This is small r. Okay, so can I say the value of small r is total radius minus depth? See, the value of small r is total radius minus depth. So substitute that here. So what will you get? F dash is equals to G, mass of this cutout portion into M2 by R minus D whole square. Okay. Also, F dash is equals to M G dash, M2 G dash. Just compare them. You'll get M2 G dash is equals to G M mass of cutout M2 by R minus D whole square. So you M2 and M2 will get cancelled out. G dash is equals to G mass of cutout upon R minus D whole square. Okay. Now, in this equation, only this term is an unknown, right? We will be given, we know the value of R. We will be given the value of the depth with which we are, calculating. The value of capital G is a constant. So the mass of the cutout we have to calculate. So here we are going to assume one thing. Okay. What is the assumption here? We are going to assume the density of earth throughout, the density of earth throughout is constant. Density of earth throughout is constant. Is that true though? Is the density of earth throughout constant? No, obviously not. If you have seen the construction work where they dig deep in, you'll see the upper layer is grainy. As you go downwards, you'll see more and more rocks, right? So this assumption is purely fictional, just to calculate. So density of earth, we are going to assume the density of earth is constant, means as we dig in, the density won't change. As simple as that. So if the density is not changing for the whole earth, density is equals to mass of earth divided by volume of earth. Or can I say mass of cutout divided by volume of cutout? Right? As simple as that. So mass of earth, what is the volume of whole earth? That will be 4 by 3 pi capital R cube. Mass of cutout, we are interested in finding that. And volume of cutout, that will be 4 by 3 pi. And the radius of the cutout part of the earth was R minus D whole cube. Hopefully this is clear. So the mass of cutout will come out to be, see, 4 by 3 and 4 by 3 pi, 4 by 3 pi gets cancelled out, right? So we will get mass of earth into R minus D whole cube divided by R cube. Okay, so we are going to substitute this value here in MC. Let's see what happens. Yeah, partition. Pages have ended. Okay, I'm just going to write it here. So G dash was equal to what? GMC by R minus D whole square. G, mass of cutout portion of earth, R minus D whole square. So G of MC, what is the value of mass of cutout? We just calculated it, R minus D whole square into mass of earth into R minus D whole cube divided by R cube, right? What will happen here? What will happen here? This square and this cube will get cancelled out. GME R minus D upon R cube. Yes or no? So this is what we are left with. Hopefully this is clear to you all. Yeah. So now just write it down, note it down. We are going to see few more things related to this. Just note it down. Okay. Now what we are interested in, this is the formula. Okay. This is the derived formula. No doubts in that. But we have to compare it with the acceleration due to gravity, right? With the value of g, which we know, which we have learned in the previous classes, which we have used in previous classes, 9.81. We have to compare it with that, right? So what we have to do then, we have to just form, see, if I take this away, g dash is equals to gme by r square, right? What we are left with, r minus d divided by, see, I just splitted r cube into r square into r. Why did I do that? Because this value is small g. If I just um if I just take this value as small g, I'll just remove this and I'll just convert it into small g. What am I left with? G dash is equals to g 1 minus d by, as simple as that. This is the formula for depth. This is the most used formula. Okay. We can derive these formulas, right? It is very pretty easy to, you just learn the formulas, but also make sure to know how to derive these. So hopefully this is clear. Just note it down. I'm giving you 10 to 20 seconds to note it down. Go ahead. Note it down. Okay. Hopefully you have noted down the formula. Now we are moving ahead. Now, what is axial rotation of Earth? We know कि Earth rotates. This is the sun. Let's say this is our sun. What does Earth do? Earth revolves around the sun, right? It revolves around the sun, and also what does it do? It rotates on its own axis like this. Earth revolves around the sun, and it also rotates around the around its own axis, right? Okay. Now what we are going to see is, we are going to see, due to this rotation, what is the effect of what is happening due to this rotation, what effect is happening on us. All right, so we are going to again bring that guy, that gigantic guy. Okay. Let's say this is the center. Okay, let me draw it with another color. Let's say this is the center, and let's say this is a vertical line. Okay, this is a vertical line. Hopefully this, you can see this. Now if I ask you what is the angle which he's making with this vertical line, that what is that angle called? That angle is called latitude. Okay. Yeah, so what we are going to see is, since this earth is rotating along its axis, since this earth is rotating along its axis like this, right, with some angular velocity omega, let's say. Okay, we can calculate omega. We'll discuss how can we calculate omega. For the time being, let's say it's rotating with some angular velocity omega, right? So this guy has a force is acting downwards on him, that is gravitational force. And also, since this whole system is spinning, a centripetal force is acting outwards, yes or no? So can't you see कि a resultant force will be acting somewhere in middle? So the resultant gravitational force on a body placed on earth is not on the center, it's somewhere in middle, right? Why is that? Because an additional centripetal force acts outwards. Is that clear? All right, now what we have to calculate is, we are interested in calculating this resultant value. Okay, if we calculate this resultant value, then we can also calculate acceleration due to this resultant value. Now what is fg here? Can you tell me what is fg? The value of fg will be given as, can you tell me? Can anyone tell me? Okay, so the value of fg is given as, or let's say, let's make it a little simpler. Let's say fg has a gravitational acceleration, since this guy is on the surface, g. So we want to calculate the resultant acceleration, right? So if we take vector sum of these two accelerations, will we get it? If we take the resultant between this G and the outwards acceleration. Will we get the resultant acceleration? Yes or no? So what is this inside acceleration? G, right? And what is the outside acceleration? That is R omega square, right? In rotational motion, you have studied outward R omega square. Okay, if not R omega square, you might have studied this, right? MV, let me write it down. Centripetal force is equals to mv square by r, and v is equals to r omega. Just substitute it here. Centripetal force will be equal to m r square omega square by r. So that will give out m omega r, right? So if I take acceleration, centripetal acceleration, mass is cancelled out. A acceleration equals to r omega. Hopefully this is clear, right? So centripetal acceleration is given as r omega. I am just substituting here. So the resultant formula is omega g square plus r omega whole square, plus 2 r omega into g cos phi. The angle between them is, acha, what is the angle between them? That's the question. See, this is outward, this is inside. What is the angle between these two? This is outside. This whole angle we have to calculate. Okay, since this line, acha, this is phi, right? So tell me, this angle, what will be this angle? This angle will be 90, right? I'm drawing a perpendicular, since this centripetal acceleration acts perpendicular to the axis of rotation. So this is 90 degree. So this angle will be here 90 minus phi. Yes or no? So just use the formula. Since this whole is 180, so we will get this as 180 minus phi, right? So just substitute the value cos 180 minus phi here. Now the value of g dash, just simple solving, g square r square omega square, r omega square, so r omega to the power 4 plus 2r omega g. What is cos 180 minus phi? Cos 180 minus phi is minus cos phi. Hopefully this is clear. So g dash is equals to under root g square plus r square omega square minus 2r omega g cos phi. Now, again, just to simplify things, we are assuming this value is very small. Why is this very small? Because the value of omega, let us calculate omega. What is omega? Omega is angular velocity, right? Omega is angular velocity. So what is angular velocity? Angular velocity is angle by time. Can we say that? Angular displacement by time. So angular displacement in one day, how much does it displace itself? Earth rotates completely in one day, right? So can I say angular displacement 2 pi is done in 24 hours. 24 hours is 60 into 60. So can't you see 2 into 3.141 divided by 24 into 60 into 60. This is the value of omega. Now, if you take 4 the power of it, don't you think this value will become very, very small? Yes or no? That's why we are going to neglect it, right? Neglecting that, what we are left with, g dash is equals to under root g square minus 2r omega square. This is square here, by the way. G cos phi. Hopefully this is clear, right? Note it down. Note down till here. This is the important one. Note it down till here. I'm giving you some time to note it down. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Now, we just learned binomial theorem, right? So, little simplification more. You might be thinking, sir, how much do we have to simplify? We have to simplify to the point we remember the formula. Okay. No assumption. Okay, let's simplify things. let's simplify things a bit more. G dash is equals to, can I say this as G square minus 2R omega square G cos phi under root. What if I take G square outside common? And I'm writing this under root as power 1 by 2. Okay. And I'm taking G square outside common. So we are left with, since G square and power 1 by 2, after going out, it will become G, right? It will be remaining 1 minus 2 omega square R cos phi, this is phi, divided by G to the power 1 by 2. Can't you see this is 1 minus some quantity x to the power n. 1 minus x to the power n. So substitute here. I'm writing down here. Okay. G is equals to G dash is equals to G 1 minus x. In the place of x, we have 2 omega square R cos phi divided by G to the power 1 by 2. Open it, you'll get a relation G minus R omega square cos square phi. This is the value you're going to get, right? As simple as that. Now, so note it down. This is important and pretty simple to be. If I see, it is simpler than the under root one, right? And it is a simplified formula. So note it down. We'll solve this question. Note this formula down. Note this formula down. Okay. Hopefully you have written this formula down. Now, using this formula, we are going to solve this question. What is this question saying? Suppose the Earth increases its speed of rotation. Suppose the rotation of this speed of the Earth increases. Okay. At what new time period will the weight of a body on the equator becomes zero? Okay. Now, on equator, let me discuss a few cases first. Okay. So, for example, this is our Earth. This is our Earth. This is a watery part of the Earth. And this is where we live, right? Okay. So, what we are going to see is, this was the angle, right? With the center phi. Now, what if the value of phi is 0 or 180? Where will we reach? We will reach, I think, at this point, the poles, right? If we take the value phi 0 or 180, we will reach pole. So substitute the value here, 0 or 180. So cos 0 is 1, right? So G dash will be equal to G. G minus R omega square, right? What if we take the value at 90 degree? Means the value of phi as 90 degree. Will reach equator, right? Will reach equator. So G dash will be equal to cos 90 is 0, G. So at equator, these two are equal. At poles, this is the value. Okay. So hopefully this is clear. Yeah. So let's solve this question. Okay. So read this question and try to solve it. I'm giving you 2 minutes to solve this question. Try to solve this question. Read this question and try to solve it, guys. Okay. One thing before moving forward, one thing I want to correct is phi is the not the angle between the vertical and this. It is the angle between these two, right? Just correct it in your notes. This is the angle phi. All right. So special cases, let me rephrase the special cases once again. So this was our Earth. This is the angle. Let's say some person is standing here. This is the angle phi. So at phi is equals to 0 degree or 180 degree. Where will we reach? We'll reach equator, right? See, at phi equals to 0 will be here, right? Or here. So this is the equator. Equator is the line which divides the whole earth into two equal parts, hence called equator. As simple as that. So at phi equals to 0 or 180 degree will reach equator. So what will be the value here? What will be the value here? G dash, we solved it here, right? G dash is equals to G minus R omega square cos phi. So substitute the value at cos square phi. So substitute the value at 0, we'll get G dash is equals to G minus R omega square. At poles, okay, at phi is equals to 90 degree. Where will we reach? 90 or 270 degree. We'll reach at the poles where I'm marking with red, right? At phi is equals to 90 degree or 270 degree, will reach poles. So what will be the value? Phi is equals to G dash will be equals to G at this value, right? So what does it mean? Let me just give you an intuition. What does it mean? For example, this is earth is spinning, right? Okay, if we are somewhere in the middle of the earth, let's say, see on the diagram, let's say here at this point where I'm pointing, okay, let's say at this point we are. So what will happen is, due to rotation, there will be a centripetal force acting on us outside, yes or no? But when we are on poles, see, when we are on poles, there won't be any centripetal force acting outwards because we are on the axis of rotation. On the axis of rotation, no centripetal force acts, right? That's why on poles you'll feel a little what do you say, heavier as compared to on equator. Okay, so that's pretty interesting. If you want to lose weight, go from poles to sorry, equator to poles. You'll lose a few negligible pounds. Okay, now let's move ahead. Let's move ahead with the question. The question is, let me erase this all. The question is, suppose the earth increases its speed of rotation. At what new time period will the weight of the body on the equator becomes 0? Okay, suppose the earth was rotating here. Let me just erase all of this. Let me make it once again. Let me see. I have the photo of earth or not. Nope, I don't. Okay. Just a sec, guys. Yeah. So this was our earth. Let me draw an earth, proper earth. So this is our earth. What is happening is, earth is spinning at certain rate. We know earth spins at a certain rate, right? Earth spins at a certain rate. But what if we increase the speed such that on equator we don't feel any weight, or we feel weightless on equator? The question is saying, if this happens, then what will be the time period back then? If what happens if on equators, let's say this is our equator, okay, so if the earth starts spinning fast on its axis, if the earth starts spinning fastly, okay, so what happens, the dhire dhire will feel the outside centripetal force will increase, right? If the centripetal force is increasing and increasing due to the rotation of the earth, if we keep increasing the rotation speed of rotation of the earth, then the value of centripetal force will also increase. It will keep increasing. There will be a point such that the earth's gravitational attraction will be equal to the centripetal force. Yes or no? We are increasing the speed of the rotation, right? So there will be a time when the Earth's gravitational force will be equal to Earth's what do you say, centripetal force. So at that time, what will be the time period they are asking us? Okay, so we are going to use that formula. What is the value of phi for equator? that is 0 degree, right? We are going to substitute it here 0. So what will we get? G dash is equals to G minus R omega square. We have to calculate time period, right? So omega equals to 2 pi by t. For one whole circle or one for whole oscillation, one whole revolution, we say time period, right? So for rotating the whole part, the angle is 2 pi and time period is capital T. So just substitute it here. G minus R omega is 2 pi by t. We have to calculate this t. G dash. Okay. So at this point, mg will be equals to m omega square r. Yes or no? At this point, we are going to see mg is equals to m omega square r. Just substitute. See, what will we get? Okay. At point A, let me write it down properly. Okay. We are going to use this formula. At point A, the value of phi is 0 degree since it is in equator. First thing. Second thing, at point A, weight of the body is equals to, since it will feel weightless, so weight of the body is 0, right? Okay, since question A, it is given, right? Weight of the body is 0. Now if the weight is given, then acceleration due to gravity at that point, apparent acceleration or the change in acceleration will be 0, right? There won't be any acceleration due to gravity at this point. Okay, so G dash, what is the formula of G dash? We saw G minus R omega square. Cos phi is 0. So G is equals to R omega square. Okay, since we substitute this G dash value as 0, right? So what will we get? Omega equals to under root G by R. Under root G by R. Now, what is the value of omega we just saw? 2 pi by t. Now, substituting the value, G is 9.81, R is 6,400 kilometers, 2 pi value 2 into 3.141, and T, we have to calculate T. It will come out to be 1.4 hours. So, can you see what does this mean actually? What does this mean 1.4 hours? Acha, current time period of revolution of Earth is 24 hours, 24 hours, right? So it takes 24 hours for Earth to completely rotate. Yes or no? Now, if we increase that speed such that it can rotate in 1.4 hours itself, we'll float on the Earth here. We won't feel any weight. So, what difference do you think we will, how Earth will differ if that was the case of actual Earth? I think it would have been pretty amazing. We can just fly off anywhere. Okay, let's move on to our next topic. Hopefully, that was clear. Now, let's move on. Let's move on to our next topic. That is gravitational field. What is gravitational field? So in the Newton's time, he imagined that around any body which has mass, around any body which has a certain amount of mass, there is a region around that body such that it can affect another mass. So let me write it down. The region around a mass where it can affect another mass. Okay, the region around a mass where it can affect another mass is called gravity. Okay, let me take an example. For example, here there is Earth, let's say. Okay, and there was an asteroid coming from very, very far away. See, at the right side, I'm making an asteroid which is coming from very, very, or meteor coming from very, very far away. Now, what will happen to the meteor if it comes in the range of the Earth? What will happen? It will experience a force, right? It will go something like this. It was, let's say it was going, uh, let's say it was going from here, right? What will happen is it will come, and dinosaurs, boom, khatam, right? So around its region, what do you say? Earth affected another mass. So we say that region is called gravitational field of Earth. So let me write it down. That is gravitational field of Earth. Hopefully this is clear, right? Chalo, let me take another example. What if I'm saying an asteroid was coming from here, and suddenly it went this side. So what can we say? There might be another mass like this, such that it attracted it and it went like this, right? So do you get the concept of gravitational field? What is gravitational field? The region around a mass by which it can affect another mass. Hopefully this is clear, right? What is the formula for gravitational field? The formula for gravitational field is, let me write it down. First of all, we denote gravitational field with E. Okay. And it is force due to gravity divided by test mass. Force due to gravity divided by test mass. What is here M, sir? What is M? What does it mean to be a test mass? So have you seen some movies in which they take lab rats and test anything on them, for example in cosmetics or whatnot? So what we are going to see is, for example, if there is a massive mass, okay, we want to calculate field due to this mass. What we are going to take is another mass which we are going to take as a test object, right? And due on this mass we are going to calculate field and all, right? So what will be the force between these two? If its mass is m1 and this mass is m2, let's say, if this is m and this let's say m and m naught, okay, and distance between the centers is r, so force will be equal to g m naught by r square. Yes or no? What will be the value of gravitational field? That will be equal to g m naught by r square and whole divided by test mass. Who is the test mass here? On whom we are testing? This one, right? So divide by its mass m naught. So m naught gets cancelled out. G m by r square. This is the what do you say? Gravitational field. Hopefully this is clear. In gravitational field, the term of our test mass on which we are testing does not matter. Okay, we are only interested in the one who is creating that field, the mass of the one who is creating that field. Hopefully this is clear. Now we are going to move ahead. Field due to a point mass. Okay, so there, what is a point mass? First of all, what is a point mass? So it's pretty simple. A point mass or point object, sorry, a point mass or a point object is a object or is an entity whose size is very less compared to its mass. Okay, for example, if I take an example, have you seen that guns? In guns, na, there are some metallic balls we use, right? So we can say that is what do you say, a point mass, right? Or let's say, let me give you an idea what point mass is. A train is a engine of a train a point mass? Can we say an engine of a train a point mass? I don't think so. It's pretty massive, right? But what if I say a train is moving from Delhi to, let's say, Bangalore? Okay, so in this distance is around, I think, 2500 kilometers something, right? So compared to this distance, compared to this dimension, the length of the train, the size of the train is negligible, right? So in this case we can say the engine of the train is what? Point mass. So do you get the idea of point mass? What is point mass? Point mass means the size, the mass, or any physical quantity compared to its dimension, it's negligible, right? So its mass compared to another mass which we are taking, which might be far away, or this object might be very small. Let's say another test mass I'm taking at distance r, and it is m naught. What will be the field due to this mass? So first we calculate what? Force. Force is equals to g m naught by distance r square. So field will be divided by test uh, test mass of test mass, mass of test object, let's say. Okay, so divided by m naught, what will you get? Gm by. So this is pretty simple. If I see carefully, for point mass, field is proportional to 1 by r square. So how will the graph of this look? Graph will look something like this, right? At r equals to 0, that will be infinity, and this whole term will become 0 at infinity, right? Hopefully this is clear. Field due to a point mass. Now, gravitational field due to a solid sphere. We are going to see gravitational field due to a solid sphere. Okay, let's start. As we saw in the case of the earth, now we calculated forces on height above, below. Same way we are going to see. For example, this is our earth. This is our earth. And okay, let me draw an earth properly first. Okay, so this is our earth. And next, what we are going to see is we are going to see gravitational field. Like, this is a solid object, right? Earth is a solid object, a solid sphere. That's why I'm taking the example of earth. Now, first we are going to see what is the value at outside. Okay, that is distance r from the center. Center say distance r. What is the value of what do you say? Gravitational field. So what is the value of force at this point? Let's say a test mass m naught, and this is a whole sphere's mass is m. So g m naught by r square. So what is the value of field? It is equals to g m by r square. Pretty simple. Outside, it is proportional. See, can I say outside this whole value field is proportional to 1 by r square? This is important to note. Outside, the field due to gravitation is proportional to 1 by r square. Hopefully this is clear. Now, let's talk on the surface. On surface, the value of small r becomes capital R, right? So E will be equal to Gm by capital R square. So on the surface, it becomes constant. As simple as that. Now, let us go inside. Let us go inside. So what we are going to do is we are going to dig. So this is at this point we went away. Okay. So what is this distance? Let's say again r. Let's say again r at this point. So what will happen inside? Inside we are going to see. Let me write it down first. First, note it down. Note idhar tak. On surface E is equals to constant. Note these things down. Note it down, guys. Okay. I'm hoping you guys have noted it down. R greater than capital R. R is equals to capital R. Now we are going to see R less than R. For this value, the electric field is, for gravitational field is given as Gm by R cube into R. Okay, so E is proportional to R. Can you see this? Can you imagine that? From center, if I'm going outside, right? From center, if I'm going outside, the force on me will start to increase. Yes or no? It will increase, increase. When I reach on this point, let's say on the surface, it will become maximum. And after that, it will decrease since I'm going away from it. Hopefully this is clear, right? So what will be the graph of this look like? So let me draw the graph. So initially, graph will be a straight line. Initially, the graph will be a straight line proportional to r, right? At this point, I'm taking E and here r. So initially, it will be a straight line. Let me draw it properly. Straight line, and when it reaches, since see, it is increasing up till when? Up till maximum at surface r equals to r. After that, this whole value decreases. So can I say proportional to r or proportional to r square. Hopefully this is clear. Hopefully this graph is clear to you all. Right? Now, gravitational field due to a hollow sphere. Gravitational field, what is gravitational field due to a hollow sphere? So again, we are taking the value of first outside, right? So this is our earth. I'm just going to make a sphere for our first one. Outside, let's say at this point. From the center, the distance is smaller. Okay, what we are going to see, it is similar, means solid or hollow or any type of sphere is there. It is same for all of them. Okay, what is the value? E is equals to gm by r square. If I take r equals to capital R, E is equals to gm by capital R square. And inside, it is very important to note, inside R is less than R. Okay, since there is no mass inside, right? All of the gravitational force is only responsible because of the mass on the surface. That's why, since the gravitational field is only because of the mass on the surface, that's why gravitational field will be equal to that on the surface, gm by r square. This is very important. Inside field is equals to surface field on the surface, means gravitational field on the inside is equals to sorry gravitational field inside is 0. Okay, gravitational field inside is 0, potential will be equal. Okay, for the time being, just remember, gravitational field inside is 0. The potential, when we get back to potential now, that will be what do you say, equal to the surfaces. Okay, so let's have a question. Okay, first let us draw the graph. After that, we'll have a question. I'll ask you a question. So okay, no, wrong color. This is the wrong color. Yep. So at y-axis we are plotting हमारा gravitational field, and at x-axis we are plotting r, the value of r. Now, inside it was 0, right? Inside electric field was 0. Okay. Now, till when it will be 0? When it will reach surface, it will have a certain value, right? That value was gm by capital R square. After that value, it will just decrease by, so I can write E is equals to 0 and E is proportional to 1 by R square. Hopefully this graph is clear. Directly, in a lot of cases, directly the graph has been asked. So please remember this graph. In solid sphere inside, let me just give you a quick revision. In solid sphere, okay, solid sphere inside, E is proportional to R. Means as you go out, as you go more and more outside the center, the gravitational field increases. But and it increases and it maximizes at the surface of the earth. After that, what will happen? The gravitational field starts decreasing. The gravitational field starts decreasing, and its proportionality is 1 by r square. Hopefully this is clear, right? What happens to a hollow object, hollow sphere? Inside electric field is 0. On surface it is maximum yet again, and after that it is proportional to 1 by r square and becomes 0. Okay, so we'll see potential tomorrow. What we studied today, we studied gravitational fields for various objects. What is the concept of gravitational field? And what if we go above the height and below the earth by digging a tunnel of depth d? So two formulas we derived and we solved the question, and we saw due to axial rotation what happens. So hopefully this class is clear. We are going to meet in the next class. Till then, keep studying, keep imagining things, keep your curiosity on, and game face on. Bye bye.
First of all, let's solve the question number 1. What is given in the question number 1? In the question number 1, it is given a process is shown in diagram which are following curve may represent the